Hello, and welcome to Facet Nation, a Gemmology podcast. My name is Simon.
And my name is Lucinda.
Hi, Lucinda. How are you?
Hi, Simon. I'm well, thanks. How are you? I'm looking forward to tonight's episode. I think it's going to be really interesting.
That's not what you just said before we came into the studio. You are a liar.
I'm massaging the truth, but honestly, guys, in terms of light and optics, this is the best it's going to get. It's fascinating for some, like Simon.
Yeah, it is fascinating. It's all really important stuff that you need to know if you're a gemologist. So you need to get your head around this stuff. So
totally true. And we'll be kind of recovering tracks from things we've spoken about before and then expanding. So it's actually a really good opportunity to consolidate your knowledge.
Yes, exactly. We might repeat a few things that we've said in the previous one of these, and we might queue up some stuff that we're going to pick up in the next one. So the next one's going to be about literally utilizing light in your testing equipment. So that's going to be the polariscope, the refractometer, and then we're going to mention reflectivity meters as well.
Yes.
Yeah, we're moving on to actual critical testing for a gemologist next. But you need this context to understand it.
Completely. And if anything feels confusing, there will be a few times where we'll point out things that you need to know to draw. Make sure that you head to Instagram at Facet Nation Gemmology. We will be posting the diagrams from our own notes so that you can kind of see what we drew, how it helped us, how we understood it. And it's also a nice inside peek into how bad at drawing I am.
Oh, I'm looking forward to that.
Yes.
Maybe we get Panny to do the drawings for us.
I know. Panny was our classmate. She's very artistic and precise, and all of her drawings were
everything
unbelievable.
Was so annoyingly neat and amazing looking. She'd turn up with bits of paper and stuff on iPads, and I'd just be like, so annoying.
And before we start, we do have one special shout out. We wanted to say thank you to Kay and her cat Jinx for sharing photos with us. We love seeing you guys and your pets. So drop us a message, drop us a line, and Kay, please give Jinx a special cuddle from me tonight. I'm sure my three cats are boys, and Simon was like, why is her cat so much more beautiful than yours?
No, I literally though, it's such a nice looking cat.
It's beautiful. She's beautiful.
I don't have any cats. I've never had a cat, but that's a really nice looking cat. My aunt and uncle have got a cat, and it's literally like a wolf. It's enormous. Is it a Maine Coon?
Yeah, they get
something like that, and it's got this fucking massive, looks like a tiger or a lion or something. It's mental.
They're also kind of wild looking Maine Coons.
Yeah, aren't they really vicious as well?
I don't think so. I think that's just temperament. But Jinx looks very sweet and lovely. She's a long-haired tortoiseshell for anyone who's curious. So by far the most beautiful of the cats.
Yes. So thanks, Kay, for getting in touch. We might do a segment, Cats of Facet Nation, if there's anybody else that fancies.
We're up to 4. So if we can hit 5, we'll do that.
If there's anyone else that fancies sending in some cat pictures, Judy has got a cat. Judy, send your
Judy,
cat
send
picture
us some
for
pics.
pity's sake.
I don't even know Judy's cat's names, do I?
No, I don't think we do. I don't know how many she has, so it's a mystery. So, Judy, send us your cat.
We're here. We're waiting.
Yeah, we want to see your cat.
All right. Shall we leave the fun stuff behind and delve into the fascinating world of light and optics, Simon?
Yes, let's.
All right. Drum roll, please, ladies and gentlemen. This is episode something. Titled
14 or something, I think. Well, the working title is Light in Gemstones.
Yes.
I might change it when we upload. But yeah,
he's going to see how he feels on the day.
Yeah. So as we know, light is a form of electromagnetic energy. Yeah. And it travels at 300,000 kilometers per second in a vacuum, and pretty much the same speed as that in air. Yeah.
Fascinating.
Visible light occupies a small section of the overall electromagnetic spectrum, which ranges from very high frequency cosmic rays, which are as dangerous as hell, to low frequency.
Quartz.
And does it?
Don't you remember we went to the Gem A conference and that man told us all about cosmic rays?
Oh yeah, in Switzerland or something.
Yes,
was it?
The mountains of Switzerland.
And we were like, how the hell are cosmic rays getting involved? Craig was really baffed by that. He was like, what the hell?
The world is an amazing place.
Yeah. So it ranges from cosmic rays to low frequency radio waves, which is basically, your radio.
Yeah, the boring stuff.
Yeah. So in Gemmology, we're mostly concerned with the visible light range, and this is the range which is detectable to the human eye. Testing for the gemstones can quite often involve higher frequency invisible ultraviolet and X-ray regions of the spectrum. and the lower frequency infrared range. So yeah, if you've got sort of lab equipment, then it's going to be utilizing some of those. Or even like you've got a little UV pen light to show your fluorescence, is that's what we're utilizing there. So these are not visible.
Yes, and by and large, most of your gem testing equipment is going to use what we call the visible light spectrum. So this is light you can see. It does what it says on the tin. And it has a range of 400 to 700 nanometers. Very important to remember, has been a question on past exams. Visible light is white. So just as you know from investigating close to where in the desert, all the colors combining together produces white light, which can then be broken down into the spectral colors. And these are red, orange, yellow, green, blue, and violet. It is your rainbow. How do you remember that, Simon?
Richard of York gave battle in vain, even though in isn't one of the colors you just said.
It exists, but it's indistinguishable.
Yeah, you're basically supposed to slot indigo in between blue and violet, but you can't really distinguish between the two, so we pretend it doesn't exist.
Yeah. And when we talk about spectrums, this will become like just something that you know. It's like the Mohs scale. Just say it over and over to yourself. You'll practice how to draw it. I'll send you some of my exciting early works that Craig just did a sad face next to.
When you drew it, did you do it to scale, like properly measure it out?
I started trying to, and then it wasn't worth doing because they kind of get it. Like if you're approximately in the range, they're like, yeah, fair enough. We know what you're saying. So what I used to do a lot that you're not supposed to do is draw the line all the way through, and then it looks like a absorption line.
Oh yeah, I've done that so many times. And if you're doing your spectrum drawing in pen and you're trying a bloody great line to divide them, then you're like, damn it.
Just do yourselves a favor, guys. Get an erasable pen.
Yes, absolutely. A friction pen. Must do that. Very
Mine
good
was
idea.
shaped like a Shiba Inu.
Yeah, it was actually.
Then I got another Shiba Inu and a panda for my second exam.
I just had the normal friction pens.
You need to bring more flair into these exam settings, Simon.
I don't have time for that shit.
I also took 2 really long bathroom breaks during both sets.
Yeah, you did. Like, just stop, leave it in the room.
I really had to pee. I was really hydrated. Anyway, so the visible light spectrum, which is the colors we just told you, we're going to break them down into their nanometer ranges. Violet is 400 to 450 nanometers. Over to you. Oh shit, sorry, I just scrolled down. Blue is 450 to 490 nanometers.
Does that mean you don't know these by heart?
I definitely question whether you need to.
I did know these by heart once. Anyway, green, 490 to 560.
Yellow, 560 to 590.
Orange, 590 to 610.
And everybody's favorite, red, 610 to 700.
Exactly right.
What is your favorite in the spectrum?
Orange is my favorite color, always has been.
It feels like it kind of also ran to me, like the orange yellow.
Right.
It's like,
I like orange because it's like sunsetty color. That's why I like it.
Yeah, but like on the spectrum, it's like deet, deet.
Oh, it's like the smallest one, yeah. So, yeah, justice for the baby.
General absorption of the yellow-orange. Get used to saying that.
Yeah, of the yellow and orange, because like the orange is big enough to just have its own general absorption.
Good talk.
So we can
like really derailing tonight.
So we can split this white light into these 6 individual colors by dispersion. We didn't cover this in the previous episode, but it's important and is a major feature of some of the most significant gemstones, particularly diamond. So this is something that we will cover in more detail when it comes to color, but dispersion works on the principle of refraction, and because each individual wavelength has a different speed, each individual wavelength bends slightly more or less across the spectrum. So for now, just keep in mind that shorter wavelengths bend more and longer wavelengths bend less. So violet bends the most upon entry into the optically denser medium, i.e. the gemstone, and red bends the least. They have differing RIs because the RI is proportionally related to the speed of travel. Does that make sense?
It does make sense. And the way that I like to remember it is, I like to make them people. So Violet is quite uptight. She's like the city girl. Right. And so she's like going on her way and she's going fast, and one thing goes wrong and she flips and she bends. Whereas Red is like my cousin Austin. He's chill, he's relaxed, his plans were loose anyway, so it really doesn't matter if he's like derailed a little bit, you know?
So that focused businesswoman Violet she just wants to get her shit done, she's getting there straight away, and then all of a sudden she goes, shit.
But because her schedule is so densely packed, she has to then like totally take a new direction.
Because the slightest little
Throws
issue
the whole thing off.
deviates her so badly because she's not built in any sort of like chill time.
Exactly.
Okay.
And so, guys,
nice.
we are talking about light as people now, but remember from our last episode, they are not people. They are waves, but also small packets of energy called photons. So don't get it twisted. If you guys want more context on this, head back to our last episode on light. It was actually incredibly interesting and fun. And just remember that light can be absorbed, transmitted, or reflected when it encounters a surface. So a lot of what we're talking about in gemmology is what happens when light interacts with a gem, which makes sense, right? So it either behaves more like a wave or as particles, depending on the specific interaction it's having with a material.
Exactly right. Yeah. So also remember that a ray of light is made of billions of waves propagating in one direction, and each wave vibrates perpendicular to its direction of travel and in all planes of orientation. Again, we discussed this in the last episode. But for these concepts, think of this. So the bit we're going to go on to next, rather than thinking of all these waves like wriggling about, just think of the ray as a straight beam.
Sorry, what are they doing, Simon?
They're wriggling about. I was having the piss taken out of me quite a lot today.
No. It's with love and respect, my friend.
Okay, good. But for these, so basically, think of this not as the waves wriggling about, but as a straight beam. But keep in mind that they are still oscillating within the beam. Yeah.
It's really complicated, this light stuff, isn't it?
No, not really.
You have to hold lots of different realities in your head at the same time.
Yeah, you do. So you kind of have to forget some bits of it to make some bits make sense. But then you also have to remember that these other things are sort of doing the other things within them.
Yeah.
But yeah, for now, just imagine light as a beam or as a ray. Yeah.
Yes.
This is going to help you understand the next shit that we're talking about.
And we're starting with how light behaves when it interacts with a surface, right? So one thing it can do is reflect. I think as a non-gemmologist, as a non-scientist, this is something that you're probably the most familiar with. As a light ray makes contact with the surface of a gemstone at an oblique angle, aka it hits it coming from the side, some of the light is reflected back, and that's what we see when something sparkles or flashes. Light is reflected at an equal angle to the angle of incidence. So as the angle increases, so too does the reflected angle and vice versa. They're always identical. And that is the law of reflection. And that lovely intersection point is the normal. It's imaginary, but it's normal.
The normal, yeah. The imaginary dotted line that goes up the middle.
Which is, perfect. I find quite fun to talk about in general essay. Whenever I say something about the normal, I feel good about myself.
Because it's normal?
I don't know, because it's it's theoretical.
I see, yeah. Hypothetical. I think that's probably accurate as well. Yeah. It's a hypothetical line that doesn't exist.
Love it. Love that dotted line for us.
Yeah.
All right, brilliant. What's next? This one took a little bit longer for me to get my head around.
Yeah, so refraction. So refraction is when light enters an optically denser material, such as a gemstone. It slows and it bends towards the normal. Yeah. So we're not reflecting equally in an equal angle now. This is now bending towards it. Just like
it's all going to go on Instagram, guys. Don't worry.
So this normal, which is the imaginary line drawn at the point of incidence where the light meets the boundary, perpendicular to the surface of the boundary, this is called refraction. So light bends towards the normal as it enters the gemstone and away from the normal as it exits. Towards, enters, away, exits. However, if the light travels perfectly along the line of the normal, straight downwards, there is no bending. It only slows.
And this is a bit what we were talking about last time. You're sitting in a ruby and it hits the wall of jelly as it enters. I don't know if that's bringing anything back. Or Simon's marching soldiers, but in reverse.
Yeah, I got it wrong. Yeah. Thanks for reminding me.
Sorry. But the degree to which the light slows down is known as the refractive index, right? You've heard this phrase before, really key in gem testing. And the value attributed to each material indicates how much slower the light travels through compared to the speed in air. So it's going to be unique for every material. Diamond, for example, has an RI of 2.42, which means that light is traveling 2.42 times slower than the light would be traveling in air. Remember, guys, repetition is good for your memory. So keep listening, hit repeat, monetize Facet Nation.
Absolutely. Just say micro and move on. So we're going to talk now about single and double refraction, which is something we didn't cover in the last episode. Yeah. So when light travels through an amorphous material, like glass, for example, it behaves in the same way regardless of its path through that material. So it still experiences refraction, but the light continues to travel as one single ray. Now, these materials are optically isotropic, and they possess no directional optical properties. Yeah, so this is exactly the same for cubic gem materials like diamond, garnet, calcite, spinel. That's all I can think of. Refer back to the crystal structure episode where we go through all of them.
Indeed, we do.
And that is due to the fact that they have a very high degree of symmetry. So whichever direction the light goes in, it acts exactly the same once it's
basically
within.
encountering the same thing in every direction.
Exactly. In every single direction.
Because the crystal's so symmetrical.
Yeah, exactly. There's no...
Or it's so fucking wild that there's...
Yeah, yeah, exactly right. With amorphous stuff, it's like so fucking... Yeah.
Chaos everywhere you look.
Absolutely. And the other version is double refraction. So crystals in the other crystal systems, so that's your tetragonal, your trigonal, your hexagonal, your orthorhombic, your monoclinic, and your triclinic, where they do possess directional optical properties, and they're optically anisotropic.
Don't get these twisted, guys. Let's talk about what happens when light enters a doubly refractive material. So basically what is happening is when light enters these materials, it is split in two different ways. This is because the crystal structure is different in different directions, because there is that little bit of adjustment in the crystal lattice depending on which way you're looking. These two rays move at slightly different speeds, which means they have different RIs. So when you put it on your refractometer, that's why you're seeing those two separate lines. And in some materials, the difference is such that you can observe the two rays in action, and that's when you're testing it on your RI, on your refractometer rather, you can see the two lines and one maybe is moving as you're spinning.
Yeah,
tell me about synthetic. Go on.
No. I was just gonna tell you about synthetic moissanite actually.
Fancy that.
So with things like synthetic moissanite, you can actually see this like with your own eyes. So when you look through the crown facets of a synthetic moissanite at the back facets, so the pavilion facets, you might see like the facet edges doubled, and we literally call this doubling of the facet edges.
Doubling of the back facets.
Yeah. And this is the same for zircon. Calcite doubles. It's got very visible doubling, so that's got a big birefringence. Tourmaline and peridot, although with sort of strongly coloured gems, it might be quite difficult to see. So if you've got quite a dark tourmaline, you're probably not going to see doubling. But if you've got quite a light one, then have a look. And if you see the doubling and you kind of like, oh, right, well, this eliminates quite a lot of things, because you need quite a big birefringence to see this doubling. So yeah, you're already narrowing your search, your options down.
Exactly. And it's not just the facets, of course. Everything in the stone is doubling. So if you've got a lovely lily pad in your peridot, you can see twice the reflection. I always like to think of it as
shadows, doesn't it? You
exactly.
know, like with those shit TVs that you used to have as a kid.
I always think it looks like when you're drunk. Like everything's just a little bit out of focus, especially like things like peridot where the birefringence is so high.
Yeah, and zircons as well can because they've got the nibbling facet edges as well. Those nibbles can look quite blurry.
I once looked in a zircon, I was like, it's a fucking mess in there.
Are you old enough to have had a TV as a kid that like looked like there was a person sort of floating behind the person? Or were TVs good?
I think TVs had advanced by then.
Okay, fine.
At least when I'm sure my parents had one or my grandparents had one. But
one of my TVs as a kid didn't have a remote control. You had to get up and change the channel.
That's very retro.
I know.
But you could sell that TV for a lot of money these days.
It probably wouldn't work.
Yeah, but it's a collector's item, a curiosity.
Yeah. So that's kind of what doubling of the back facets looks like, ghosting on your shit old-fashioned TV. So these two rays that have divided and become this one ray that's now become two rays in your optically anisotropic material behave in a tidy fashion, and they are plane polarized. So they are always at right angles to the propagation direction, and then always at right angles to each other. So if you can sort of try and
again, we'll show you on Instagram, guys.
Yeah.
There's blue, there's red, there's wiggles.
Yeah, and I've just been mentioning birefringence. So the numerical difference between the two RIs is known as the birefringence, and we'll explain this a bit more when we get into the refractometer.
But first, let's talk about uniaxial versus biaxial, and I've got bad news for you guys. You do have to memorize which stones are which, it makes it so much faster and easier to know a little bit about what you're looking for. So Simon, tell me, what is uniaxial?
So the more orderly of these anisotropic systems, so that would be I always think of them as like
descending degrees of order.
Yeah, and I sort of imagine them in my head written in an order.
So we're now at like lawful neutral, I would say.
Yes. So the more orderly of the less orderly ones, which is the tetragonal, the trigonal, and the hexagonal, split the ray into two with different speeds. However, one of the rays has a constant speed. The other ray varies its speed dependent on the vibration direction through the crystal structure due to differing lengths of atomic bonds. So these are known as uniaxial materials. One ray has a fixed Ri, the other ray has a variable Ri.
Yes. Biaxial materials, on the other hand, we're talking maybe more chaotic neutral, maybe a little lawful evil moment going on. These are the orthorhombic, monoclinic, and triclinic systems, which means basically both rays have a variable speed. It's chaos in there. Neither ray has a fixed or constant Ri. So in all anisotropic materials, there's at least one direction in which light travels without splitting in two rays. That is what Simon was talking about. It's the optic axis. And in this direction, the stone will behave as if it were singly refractive. In the other directions, that's where you can get a sense of a stone's optic character.
Yeah. So the definition of the optic axis is a direction of single refraction in a doubly refractive material. So uniaxial materials, they have one optic axis. So that's your first three, your tetragonal, your trigonal, your hexagonal. So they've got one optic axis, and this is always parallel to the c-axis. So that's the long stick, the long north to south stick. It's not always long, but most of the time it's long.
It's really helpful to actually practice getting to know this on a stone like tourmaline, where the c-axis is exactly what you think it would be. It's straight down the barrel of that long crystal.
Straight down the barrel, yeah.
So you can go on.
And that's its optic axis. So and also like for things like aquamarine, if you see the rain and you want to find the optic axis, then look straight down the rain. So the tubes, the hollow growth tubes, look down the tubes, and that's your optic axis.
And just remember, guys, when you're testing, always be turning your stones, because if you do find an optic axis, your tourmaline is going to be looking a lot like a spinel.
Yes, exactly. So make sure you're not taking your Ri in that direction, because you're going to get one edge and you're going to be...
And you're not doing your polariscope.
Problems. Yeah, you've got to rotate that stone in all directions on your polariscope. But more on that when we talk about how to use that and how,
Exactly. So there are a couple of tricksy motherfuckers who use this tendency to their own advantage. Simon, tell me about some diamond simulants.
Yeah, so your diamond simulants, like your zircons and your synthetic moissanites, because they have got quite large birefringence, and you're going to see the doubling of the back facet, that's a dead giveaway that it's not a diamond, because diamond's cubic. So you're definitely not going to see that, because there is no birefringence, because it's singly refractive, right? So you're always going to want to fashion that material so that so you can't see the doubling through the table, yeah? Because you don't want to be able to just look straight in the place where you're supposed to be looking and see the doubling of the back facets.
You want to try and hide it, at least.
Yeah, you want to try and sort of shift this. So you say, you're not going to be able to see that.
But there is one telltale way, and that is to look through the kite facets.
Look through the kite facets, look through the crown, look sort of diagonally and across, and that's where you're going to see the doubling, because, they're going to have this optic axis bang through the table, so you're not going to be able to see that.
Now, biaxial materials, not wholly chaotic, but pretty close, because they have two optic axes which are never parallel to the c-axis, so they are just doing their own thing.
Yep, all over the place, so you can't orientate. So there's some pretty heavy explanation of this and how you can work it out, which we are never going to go into, just to let you know. So
maybe if we really run out of material.
Yeah, maybe we'll come back and tell you all about how to find the bloody optic axes in biaxial materials.
All right, So
the next thing we're going to talk about is actually really interesting and really exciting, and it's total internal reflection, which is...
This is pretty interesting because it's so key to how stones perform. So when you look at a stone, a diamond is kind of the classic example, but also colored stones. And the light is just flopping out of it and it's so depressing, it's because the cutter has not utilized this in perhaps the way that they should. So it's something you can really see in the stones that you're looking at.
Something Arya spoke to us about. He was talking about Snell's law and like making sure that all of his angles were perfect so that he returns as much light as possible. Now he can't cut particular stones because they're not going to return the light. So this is vitally important. And he can just tell
based on a stone's RI what's going to work and what's not going to work, which I think is so amazing.
Exactly. So now we're talking about light basically from within exiting the material. So as light passes from a medium of higher RI into one with a lower RI, as in a gemstone back into the air, it is bent or refracted away from that imaginary normal. And as the angle of incidence increases, so too does the angle of refraction. Yeah? So we're getting it. If we're angling up, we're also angling further away from the normal. So there is a critical, and I use that word very deliberately, at a certain point, depending on the material at hand, the angle of refraction will be 90 degrees to the normal. Yeah, so light will pass, instead of coming up and out and bending away from the normal, at a certain point it's going to run directly along the interface between the two media, along the surface boundary, yeah?
It bends just enough that it gets onto the track, basically.
Yeah, it's just going swoosh. That was my skating along the top of the gemstone sound effect.
I liked it.
So this angle is known as the critical angle.
And this is super, super important because when light strikes the boundary, any angle greater than the critical angle, no refraction occurs at all. So the light is reflected entirely back into the gemstone. That is total internal reflection. And it just keeps, if you cut your stone right, it just keeps bouncing around. It's almost like Labyrinth, where they try and trap the baby in the magic world. That's what you're trying to do with light. Once it enters the stone, don't let those motherfucking carbuncles or whatever leave. Keep them in there.
It ain't getting out. Yeah. So yeah, that's what you want. You want stuff bouncing around inside, and you're trying to direct the light to come out where you want it to, not where it wants to.
And you want it to come out at somebody's eye.
Yes. So
they look at it and they say, "Gosh, that's so sparkly."
Wow, look at that. And this brings us on to brilliance. And brilliance is exactly what it says. It is brilliant.
Wow.
Now, we're mostly concerned with diamond here, as its unique properties give way to exceptional brilliance. You're not going to see a gemstone that really has as much brilliance, quote unquote, as a diamond.
And these are, Craig always used to say, these are the white flashes that you see coming off of a diamond. The rainbow flashes we'll talk about a little later.
Yeah, so brilliance is like reflected by a faceted gemstone, and it includes the surface reflections and those internal reflections that we've just been talking about.
And you have to fashion stones very specifically to harness this to its best effect. I mean, these days, lasers are involved, computers are involved. Arya was saying when he's fashioning stones, he can like plug in a formula and a machine will do it all for him. But essentially what you're trying to do is return as high a percentage of light back to the eye as possible. And this is a crazy stat. If you perfectly cut and proportion a diamond, you can return 92 to 93% of the light back to the viewer in the face-up position, which is absolutely insane and kind of speaks to why diamond is so... I mean, I used to hate diamonds, and now I look at a diamond and I'm like, yeah, fucking fair enough.
Yeah, exactly.
They are so beautiful.
So people are like, oh yeah, diamond. Why is it so special? We can just create them in a lab. This is nuts stuff. It's mental that these things are just like...
And it's just carbon, man.
And they're like so fucking old, and they took such a long time to grow, and we have to respect that, I think.
I agree.
And we have to respect...
also the craftsmanship of the cutting, because if you cut too shallow, the light won't return. It just falls out too deep, and it's like, no, it kind of drowns in the stone. The stone gets all kind of murky and dark and lifeless. And then the tolerance for the pavilion facets is so low, it's like 1 or 2%. And if you fuck that up, like, your stone's dead in the water, man.
Literally, yeah. So it's tiny, tiny, tiny little fractions of degrees, and the whole thing can be way off.
And you do need to learn your tolerances, by the way. We'll talk about that in a diamond episode.
Yeah. So, but we will just mention now that diamond has a very small critical angle of 24 degrees and displays a higher degree of brilliance over a greater range of viewing angles than other gemstones, which is what makes diamond special. Yeah. So it's got that perfect sort of balance of the RI and the critical angle and things like that. That's just making it sort of do all these mad things.
Yep. And when you play it right, light will enter your diamond and through the crown facets, and then it will reflect internally over and over and over again through a hall of mirrors, and then it will bounce up out of the windows and the crown facets on the opposite side. So it's doing like a full turn. It's hitting every facet, and then it's returning to your eye.
Yeah, so what you said just there is I like to think of the crown facets as windows and then the pavilion facets as mirrors. So if you kind of get that into your head, the light comes in through the window, bounces off the mirror, and then back out through the window, back up to your eye.
It's giving Versailles.
It's giving, sorry.
Versailles, the Hall of Mirrors, where Marie Antoinette was married.
Yes, after.
Because that went so well.
Not after she was beheaded, I was going to say.
Before.
Very much before
Sometime
that.
before.
Very much before that, yeah.
So RI and critical angle are closely related. Simon, tell us how.
Yeah, so a greater RI means a smaller critical angle. However, if the critical angle is too small, light struggles to escape where you want it, so through the windows, and the gem cutter would need to cut the stone to an impractically shallow depth to achieve brilliance and encourage light back to the viewer's eye. So, as we were just saying, diamond strikes that sort of perfect balance. It can be a sort of normal size, if you like, a normal depth, so that it can be set into rings and not be like a mile off your finger or be like some flat, dangerously precarious gem that's going to break. It can be, everything sort of in proportion, if you like.
And there's a really good test for this. It does rely on stones being unset, which I see less in the trade than I did at Gemme, certainly, but still really fun. And I think a good way to impress people at parties is called the read-through test. So you draw a line on a piece of paper and you place a well-cut diamond over the line, table down. And when you view it from above, the line won't be visible because the light that's entering the stone is being internally reflected so many times that it's blurring the image of this line. Whereas a CZ, God bless them, I have a CZ tennis bracelet. When it sits next to a real diamond, it looks really sad, but on its own, it's okay. I love you, I'm sorry. So a CZ at the same proportions, which obviously has a lower RI and a higher critical angle, is going to leave the light untouched enough that you're able to see the line through the stone. Telltale sign.
And it's literally just like a really easy test. If you go like, something looks a bit off about that, draw your line, have a look at it. You see the line. It's not a diamond.
Yep. And I told you guys once that of all the, is it the 5 C's? Cut is my king. Simon agrees with me here in the case of diamonds.
Cut should always be your king in the case of diamonds. Yeah. So if anybody, a poorly cut diamond can actually not only affect how it looks, but also affects the value, because it's completely pointless. If you go out and buy a D color IF internally flawless diamond or something that's VVS, something that's going to cost you loads because it's like super rare, if it's cut badly, a perfectly proportioned FSI1 could very easily look much sparklier, much brighter, have more brilliance, effectively look better
and be more impressive. And I feel so many people buy diamonds and they get shit diamonds because they want a big diamond. A smaller, better cut diamond, even if it's got poor quality, maybe poor color, is always going to get more wows. So even at a pure mercenary level.
Yeah, I mean, it depends where you do your research as well, because some places you might be sort of, I'm thinking of buying a diamond, let me look on the internet. And some places might bang on about how it's important to have high clarity, how it's important to have high color. I mean, the color aspect is obviously a thing, but you might prefer it to have a bit of a tinge. And the clarity is obviously important because you don't want things, any sort of interruption of the light is going to cause an interruption of the light. So if you've got loads of inclusions, light's going to bounce off them and not come back out your window. But effectively, you want to be focusing on how well cut the stone is, because that's what's returning the light, and that's what's sort of, you know, that's what the gem cutter spent all that time doing. So again, something. Well,
what I've noticed, especially if you're buying diamonds for other people, engagement rings, some people see color, some people see clarity. Everybody sees cut.
Yep.
So, you know, you can figure out color and clarity down the line, but always prioritize cut. Thank you for coming to my TED Talk.
I enjoyed it.
All right, now another fun kind of more diamond specific, but you've dropped some alternates here. Let's talk about fire.
Yeah, so fire is also very important. So my favorite fiery gemstone, which we mentioned, did we mention it?
We did.
We mentioned it in the Aria episode at the end, because I want him to cut one for me in his amazing Void Reaver cart. Is a Sphene. So
love a Sphene. Although I was slagging off Sphenes because I find them confusing.
What do you find confusing about them?
I think I find them confusing because they shouldn't have as much fire as they do according to like the crystal family they're part of. They're like a total standout. They're very much their own thing.
So the reason I like them is because you can get them in colours that are sort of quite metamic zircony,
You
but
love a metamict.
but you're getting the sort of mass dispersion, the mass fire out of it. So it's kind of the best of both worlds. I mean, I like the metamic zircon because it's sort of a bit dull and dying and decaying, but I
And
also
yet-
like the Sphene because it kind of reminds me of like how the zircon used to be in his younger days.
Oh,
A Sphene kind of feels like a young sprightly metamix.
yeah. I love that.
Yeah.
My favorite fiery stone is a demantoid.
Okay, yeah. Also that same sort of colour.
Yes. And also, I think equally like has durability issues. Like, I love gemstones because they can't do everything, okay? They can only do some things, and you're just going to have to accept that. And demantoid is beautiful and it can do the fire, but it is not fucking with daily wear. It is not going to be in your ring. It doesn't want to stick around that long. Like, it's done.
No, and like I suppose you could argue that a red diamond or something kind of ticks all the boxes, but like
That's why they're a gajillion dollars a
you're
carat.
fucked if you're trying to get one because you need to be a multi-billionaire. So yeah,
We'll leave that to Bezos.
yeah, exactly.
But anyway,
Yeah.
what is fire now that we've talked about it for ages?
So we're talking a lot of shit tonight. Fire relates back to dispersion and basically is when flashes of the spectral colours are seen dancing in front of your eyes. So we'll talk again more specifically on this when we cover colour and diamonds in greater depth. Yeah, it's basically the spectral
the
colours.
rainbow.
Yeah, the spectral colours having a little dance.
So beautiful. But there are other optical effects, guys. Diamonds don't get to have all of the fun. We have mentioned these before way back at the start, but we're going to get more specific about how they work. And again, reiterate, repetition is really key with these because the more that you hear it, the more you hear people talk about it, the more you'll be able to sort it out in your own mind because they sound the same. A lot of them start with A's. A lot of them are like the same but slightly different. So let's get into it. What's up first?
First up, we have Aventurescence.
Woot,
So
woot.
Aventurescence can be seen in the aptly titled Aventurine Quartz.
Somebody knew what they were doing there.
Yeah, no, they've really fucking tried out with that one. And Feldspar Variety Sunstone, which is a much better name.
Agreed. And Aventurescence is basically a spangling or a glitter effect. What's happening here is light is being reflected off of shiny and reflective internal inclusion. So this isn't about the material itself. It's not about the stone and its RI or its angles. It's about inclusions in the stone. Not half as complicated or technical as total internal reflection, but it does take place internally within the gem. So basically, instead of pavilion facets acting like mirrors, small platelets or a fine dusting of inclusions are your mirrors.
Yes, you've literally got like little slabs of mirror inside your stone, which is just the light's just bouncing bosh straight off that. It's very simple, but it creates a very nice effect when they are all sort of collected together. So in Aventurine Quartz, the cause is platy mica.
Woo!
What's our slogan to do with mica? Just say mica and move on.
Yes.
So the platy mica is planar orientated and parallel to the base of the fashion gemstone, so that the flat surfaces are uppermost of your platy plates, and when light hits them, they return that light back up and cause a lovely sparkle. Actually, it's the mica that causes the green colour in Aventurine Quartz as well, because if you didn't know that Aventurine Quartz is green.
Yes, and the same is kind of going on with Feldspar Variety Sunstone, except the inclusions that cause this spangle is hematite. So there's another version of sunstone, which is a finer, more shimmery spangle. This is caused by copper. It's called Oregon Sunstone. But Simon, it's not just from Oregon, you learned, apparently.
No, so at the GEMA conference, Rosie Young, who did a talk and I had a chat with, is doing a whole sort of research thing on Oregon Sunstone, but from Ethiopia. Yeah. And when I was talking to her, I asked her what we should be calling Oregon Sunstone that isn't from Oregon, but actually from Ethiopia. And she said, I'll work on that. So
Right.
she doesn't actually have an answer. So I don't know if we're calling it like,
Sunstone.
I don't know if we're calling it like Oregon type sunstone or if we're calling it like Ethiopian sunstone.
Or is it going to be like copper bearing sunstone? Or is it going to be...
I told her, the conversation I had with her was, listen, Rosie, you need to come up with a name for this, and we need to have you on the podcast and we can discuss it. So,
also, shout out to Oregon Sunstone just generally. It's so beautiful.
honestly one of my favorites.
So
Orange,
beautiful.
which is, as we've just established, one of my favorite colors, and like the shimmery effect as opposed to like the sort of straight spangle.
It looks
is
like
how,
ethereal.
Yeah, that's how I differentiate them. Like there's a shimmer or a spangle.
I like that. That's really smart.
And so the Oregon stuff has a shimmer.
Yes, as opposed to, and it is fun to see the spangle, but once you see the spangle, it's like, okay.
Yeah, and I suppose just because we're talking about Aventurescence, we should mention Goldstone.
Even though Simon's a hater.
Even though I'm very much a hater. So
It's
you can
man-made
tell us
glass,
about
guys.
Goldstone. Yeah.
Simon can't stand it. Man-made
No.
glass, it's extremely spangly. It's usually in kind of obscene colors. They sell it like at souvenir shops. And the spangles are caused by copper platelets that are added to the glass as they're making it. So they just chuck a shitload in. There's no specific orientation. There's no underlying structure. I would say usually, maybe I've not seen any good Goldstone, but the material itself is much more opaque. There's none of that like transparency. There's none of that underlying structure. It's just a big sparkly pink mess.
Yeah, the blue stuff is really offensive.
I don't mind it so much, but you know, I'm from California, so it's all over Venice Beach.
Especially when they like Facet at the top of it. It just looks so shit.
I think it's quite funny when they make it brown, like it's going to pass for anything like quartzy.
Yeah,
like, just turn it brown. Like, what?
Come on, man. Like, seriously, if you're like even thinking of being a gemologist and you can't tell the Goldstone just by looking at it, then like sit down, have a word with yourself.
We all start somewhere, Simon.
Look in your spangly mirror, and you need to understand that stuff is like, yeah, so identifiable. Is
once you see, like all things, once you see the real version and then you see the simulants, there's so many times I'm just like, oh, fuck, that's so bad.
Right, yeah, that's what it's supposed to look like. Yeah, it's so true.
I have a bag of plastic amber beads that I'm looking at right now. They're pretty bad. But if I hadn't known any better, you know.
No, yeah, that is so true. Yeah, like you can only know something you know.
You don't know what you don't know.
And that's what we're here for, to help you know stuff.
And we're also here to talk to you about Chatoyancy, aka the cat's eye effect. I think, actually, I was going to say it's overrated, but I disagree. I'm not going to take that stance.
No, I think that's really unfair. Top quality cat's eye chrysoberyl. Like,
beautiful. And that's what I was thinking about as I was saying that. And even like cat's eye tiger I'm into. So what is it?
So basically it's a bright, narrow band of light that moves across the surface of a gemstone due to multiple internal reflections. Chatoyancy has a very strict criteria.
And you have to memorize it, guys. You have to memorize it word for word.
The chatoyant narrow band of light. Take it away, Lucinda. Tell us about the criteria.
Number 1. Long, thin, quote, needle-like, quote, inclusion. So these are crystal needles, fibers, or hollow tubes.
Yes. Those inclusions, they must be parallel in one direction.
They also must be in sufficient abundance. No other details, just sufficient abundance.
Yes. So sufficient, I suppose, it's not sufficient if it's not causing a cat's eye.
Yeah.
So once it's sufficient, it's sufficiently doing the job.
We're not putting a number on that.
No, you can't put a number on it. The fucking thing's massive. You need more, don't you? I shouldn't say massive, very large. Don't want to get confused. Don't want to get confused.
All right, what's next?
Okay, so the gemstone must be fashioned with a domed surface. Yeah, the domed surface confines the bright light to a single bright narrow band that moves across the dome of the stone as either the stone, the viewer, or the light source moves.
And the base of the stone must be fashioned parallel to the inclusions. Put that last 30 seconds on repeat, guys, because it has to be like, you'll get to a point where you're just rattling this shit off, I promise you.
Yeah, you want to be able to sort of reel that off. You want to know how to describe that. You want to know how to draw it too.
Yeah. And famous chatoyant gemstones. We just mentioned one. The most famous is cat's eye chrysoberyl. You're looking for a lovely milk and honey where you've got like a kind of golden stone with a milky, lovely chatoyant effect.
Yeah, and that milk and honey effect sort of happens either side of the narrow band.
Very beautiful. Even a hater like I must acknowledge.
Yeah. So this narrow band, this reflected narrow band of light appears at a 90-degree angle to the direction of inclusions. Yeah. So the stone needs to be fashioned
band.
with the needles running across the width of an oval. So if your stone's an oval cabochon, the needles need to be running across the width for the light, the band of light, to run across the length.
Yeah, so don't think of the cat eye effect running down a single inclusion. It's actually running down the whole row.
It's running across the inclusions.
Yeah, it's running across the row. You will have to draw that at some stage, I'm sorry to tell you. So where do we see this? We see it in Chrysabella, as we've said, but also tourmaline and quartz. But any gem material can show this effect if criteria is met. Didn't we have a really shady chatoyant stone?
Yeah, we did.
It ended up being something that pissed everybody off.
It was a cat's eye quartz.
Yeah.
You can see the cat's eye by shining light through it. If you shine the light through it, the cat's eye works, whereas normally it's reflected light. So it's like you need to focus your light source and shine it on and reflect it. But actually, the quartz one, you can shine light through it and it still works.
It was in a practical, and we all were losing our fucking minds about how unfair it was. And then somebody flipped open the handbook to the quartz page, and there was a picture of it. Right
literally
there.
A picture of the same fucking thing. You're like, you bastard. But it's these sorts of errors that mean you never do that again.
Nope.
Never make that mistake again. Yeah.
All right. Chatoyancy's a gaudier cousin, perhaps? Asterism.
Do you think it's gaudier, or do you think it's just a bit more multifaceted, a bit more trying a bit harder?
Yeah. I mean, attention seeking.
100%.
Guys, it does what it says on the tin. It is the star effect, fundamentally the same as Chatoyancy, with the same criteria, except it needs more than one set of needle inclusions in two or more directions. So if you think of Chatoyancy, the needles are going like this. In Asterism, they're like, what? Would you say?
I've got nothing to say. Yeah. Apart from what? Yep, exactly that. Yeah. So, yeah. You've totally thrown me with your dance and just, yeah. So did you say that it needs 3 sets of inclusions?
I think I said 2, at least 2.
At least 2. Okay, fine. Yeah. So 2 or 3. And remember that light is running at 90 degrees to the direction of the inclusions. Yeah. So
across, not along.
Yeah. So in order to get like a 6-rayed star, if you like, which is going to have 3 intersecting narrow bands of light, we need 3 sets of inclusions. So if you've got one set of inclusions running east to west, one set running diagonally northeast to southwest, and another set running southeast to northwest, that will produce a 6-rayed star with the 3 bands intersecting in the center at 120 degrees to each other. Now, this is in a perfect scenario, which is almost never achieved unless you've got some super, super, super high value, like
crazy
star
shit.
sapphire or something, like the Star of India.
Yeah. And as Simon says, corundum varieties tend to show 6-rayed stars. They're the most highly prized and valuable. You can see some amazing stuff I think Berganza is actually having a bit of an asterism moment. They seem to have a lot of star sapphires and rubies in their window. So if you are in London, check it out. Outside of auction houses and big safes.
And
if you
museums, actually.
Yeah, if you like perfect, clean, beautiful stars, you're probably looking at something fiber optic, which we'll tell you about later.
Yeah, you're looking at like synthetic star sapphire or something like that. Yeah, these things are generally a little bit imperfect, which we kind of like. We like things that are slightly not totally perfect.
It's how you know they're natural.
Exactly. Yeah. So that's why you should be suspicious, because if it's too perfect, it probably is too perfect.
If it's too good to be true, it usually is. That's the gem trade philosophy I have found.
Yep. And then we are going to just briefly speak to you about Labradoressence, Asterism, and play of color. So these effects are due to interference, dispersion, diffraction, and scattering. So we're just going to mention them now, but actually these are going to come into play a lot more when we talk about color, which is going to be a series of episodes that's probably going to take a long time, because there's a whole shitload of stuff that we need to tell you about, and it's very complicated, so we're going to try and break it down into as manageable bits as possible.
Neat, manageable bits with outside expertise and lots of help. But it's, again, with all of these A's, Asterism, Labradoressence, like, just start getting used to saying these words, differentiating the ones that you already know, and then we will do a deep dive into all of these. And once you
Yeah.
start to understand them, they're quite fun.
And when we do that, we'll revisit the fire and the dispersion as well, because that's all to do with light and splitting of lights and like colour, really. So colour's going to be a big one. You're going to have to, prepare yourselves for that. But yeah, anyway, that's more or less part 2 of the light episodes. There's one more to come when we're going to talk about, as we said, utilising it in testing equipment. Hopefully that's helped. Hopefully you've got a bit of an understanding of this concept. And
we've talked you through the really, really heavy theory. Next week will be the practical applications. You can see how it affects your gem testing day to day.
Yep, exactly that.
Any news and views? It snowed in Hatton Garden today, so shout out to anyone who's around to see it.
Yeah, well, so I was around to see it, but didn't see it. So that's kind of weird.
I'll send you a video.
Yeah, please. I've just experienced the snow through your
Second
video.
hand.
Thanks.
We do what we can. Thank you so much for joining us, everybody. Like the podcast, subscribe, follow us on Instagram. We're going to be posting more frequently, dropping some knowledge on there, and also try to get our TikTok up and running if and when I can log into our email.
Don't forget, we've got I've got a t-shirt now, which you have possibly, no, you won't have seen. I will reveal that when we do an episode in the future, maybe next week. So I've got a t-shirt now. So if anyone wants a t-shirt,
yeah, if you guys see any merch, hopefully you've got some of our free stickers that we're dropping. If you want any other merch or want something mailed to you, let us know and we can make it happen.
Stay in touch, get in touch. Yeah, thanks very much for listening.
Have a good evening, guys. And again, just hit replay while you're sleeping to learn all of those.
We still need to do those shipping forecast things because that's, absorbing, repeating.
Simon's going to get on that over Christmas break. Don't worry.
Yeah, okay.
All right. Bye, guys.
See you later, mate.